Hey, it's Mr. Nelson again. Here we're going to do another stoichiometry problem. Again, mass to mass. This time we're working on practice sheet number 4, problem number 2. So as we notice, we don't have the steps that we have to go through for stoichiometry in this worksheet. So you have to make sure that you, again, understand those steps, know how to work. We are going to go from mass to mass. But one of the first things we have to do is we have to make sure that in order to go from mass to mass, we have to do our molar ratios to figure out what our molar ratio is in each one of those. How do we do that? We balance chemical equations. So we have to make sure that we figure out what the equation is, and then we have to balance it. So we have to figure out that skeleton equation. So let's go ahead and read the question. When ethylene is burned in the presence of oxygen, it produces carbon dioxide and water. If you start with 45 grams of ethylene, which is dicarbon tetrahydride, how many grams of carbon dioxide will be produced? So we start off with ethylene. Here's our thing. So ethylene in the presence of oxygen. So ethylene is going to combine with oxygen. We're probably going to have some type of catalyst in there, but remember, catalysts are not used in the reaction. So probably heat in this case. We're going to burn it. So we're going to get heat, and it's going to create carbon dioxide and water. So let's look at the first one. We have ethylene. Well, it's dicarbon tetrahydride. That's another name for ethylene. Now, when we do this, we know that this is a type 3 because of the prefix. So when we go ahead and start off, we're going to have carbon, but how many carbons are we going to have? We're going to have 2 carbons. That's what the di means. So we're going to put our subscript there of 2. And then we're going to have hydride, which is hydrogen, and tetra means 4. So we're going to put hydrogen, and then we're going to put 4. Now that's going to be burned. There's our catalyst, our heat, in the presence of oxygen. So we're adding oxygen to the mix. And so that's going to be another reactant. Now the thing with when we have oxygen or have any element all by itself, the question that we always ask is it diatomic? So again, we can look at our periodic table. We can figure out whether or not it's one of the 7 that are diatomic, which they make a 7 right here in the periodic table. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, plus our hydrogen, which is hiding over here, are diatomic. So oxygen is diatomic. So let's go back to that. And so we have to make it diatomic by putting a subscript of a 2 with it. Now, what is that going to do? That's going to yield carbon dioxide. Now, carbon dioxide is another type 3 compound. And remember, if there's no prefix in the first one, that means that there's only one of them. So we're going to put carbon. Then we have dioxide. So we have oxygen. Di means we have 2. So we're going to have a subscript of 2 in there. Then we're going to have our water, which we all know that the formula for water is H2O. Remember, water is also called dihydrogen monoxide. So there's our skeleton equation. So now we have to go ahead and balance it. When we balance it, we're going to go ahead and put all the elements that we have on each side. So we're going to have carbon, we're going to have hydrogen, and we're going to have oxygen. Now that's what I have on this side. I have the same thing on this side. Oops. So we're going to put it over there. So we're going to have carbon, we're going to have hydrogen, oops, and we're going to have oxygen. So how many do we have on each side? Well, carbon, we always go by the subscripts. Remember, we don't have any coefficients in there yet, so we're going to go by the subscripts of each one, wherever it's at. So carbon, I have 2. Hydrogen, I have 4. So we'll put a 4 there. Oxygen, we have 2. On this side, I have carbon, I have 1. Hydrogen, we have 2. And oxygen, I have 2 here plus this one over here, so we have 3. So we're going to save oxygen at the end. And here's again a little trick that I'd like to help you out with, is that oxygen over here is all by itself. So all we have to really do, since it's diatomic, is make sure that it's even on this side over here. So if we make sure that oxygen is even on the product side, we know that the reactant side we can put a number or a coefficient in there to figure out whatever it is. So we're going to save that to the end. So we're going to start off with our first element, which is almost always like I would like to start off with. So I have carbon right here, and I have 2 of them. So I have to make 2 over here. Now I cannot just put a 2 here. Again, I can't change the subscripts there, but I can put a coefficient. So I can put a 2 right there. So that changed my carbon now to 2. Okay, so we'll get rid of that. But it also changed my oxygen. So now I have oxygen. I have 2 oxygen here twice. So I have 4 there, plus this one over here. So now I have 4 plus 1 is 5. So now I have 5. But remember, I'm not going to chase the oxygen. I'm going to go back and I'm going to chase the hydrogen. Okay, because we said oxygen left by itself. Plus oxygen's in 2 different spots here. So if I leave it to the end, it might just work itself out. Or hopefully it was. So I have 4 hydrogen here. I need 4 over here. So what do I have to do? I have to put a coefficient in front. So if I put 2 times 2 is 4. So now I just change that to a 4. So now my hydrogen is balanced. But that also changed my oxygen. I have 2 oxygen here, right? Times 2 is 4. Plus my 1 times 2 is another 2. So 2 plus 4 is 6. So that changed that to a 6. Okay, so now I have 6 oxygen. So now I just have to come over to this other side, and I have to make sure this is a 6. So I have to change my coefficient. What times 2 equals 6? Well, if I put a 3 in there, 3 times 2 equals 6. And that changes this to a 6. And I can get rid of this right there. And so now I have 2 and 2, 4 and 4, 6 and 6. Let's go back up and double check in our equation itself. So I have 2 carbons right there. I have 2 carbons right here. I have 4 hydrogens right here, and I have 2 hydrogens times 2 is 4 there. Now oxygen, I have 6 oxygen on this side. So I have O2 times 3 is 6. And then I have 2 times here is 4, plus my 2 that I get over here is 6. And so we have a balanced chemical equation. So our molar ratio, okay, is going to be 1 to 3 to 2 to 2. Again, would like you to go ahead and make that bold and change that to a nice bright color. So now we have our molar ratio. Once we have our molar ratio, the next thing is we have to do our stoichiometry, and we always start with the number of grams that are in the equation. So we're starting with the number that's in the equation. In this case, it's 45 grams of ethylene. So we're just going to scroll down here, and we're going to put 45 grams of ethylene, which is right here. That's ethylene. So we're going to copy that, and we're just going to go ahead and paste that right there. Now again, the next step that we do is we're going to do 3 steps according to our stoichiometry map. And if we go back down to our stoichiometry map, and there we go, there we have it. So we're going from mass to mole. So I put 1 mole on top, and we'll put the molar mass of whatever we're talking about on bottom. Then I'm going to put my molar ratio, and then I'm going to do just the opposite as we did at the beginning to get from moles back to grams. So let's go ahead and go back to the problem. So we're going to put our times in our line. Remember, we're going to put 1 mole on the top, 1 mole of ethylene. So we're going to paste that in there. Okay. Then what we're going to do is we're going to go to the bottom. We're going to put our grams of that in there. Now again, our grams of this, and how do we figure that out? We have 2 carbons at 12 each plus 4 hydrogens at 1 each. So we're just going to add those together. So we have 2 carbons, so 12 plus 12. And then we have 4 hydrogens at 1 each, so we're going to just add 4 to that. So we end up with 28. So we're going to put right down here, we're going to put 28 grams of this compound, okay, of ethylene. Then we're going to go back up and do the same thing, but this, remember, we're going to start with the one on bottom, and we're going to put our moles of that on bottom of ethylene. And how do we get that? Well, our moles of ethylene is going to be right up here. Here's ethylene. Here's our balance equation. If we don't have our balance equation, we're not going to have this ratio here, because remember, 1 mole of ethylene equals 2 moles of carbon dioxide. And that's where we're going to go. So we're going to say 1 mole. So that number right there goes down here. So we're going to put a 1 in there. Okay. And then on the top, we're going to put 2 moles of carbon dioxide. So I'm just going to go ahead and copy this. And we're going to place that right there. And we have to put moles down there. Okay. And I'm going to underline these real quick just to... Okay, so we have that underlined. Now, notice I'm going to get rid of this. So I have it in moles of carbon dioxide. So I have to get it from moles of carbon dioxide to grams, because that's what the question asks, how many grams. So we're going to start again. We're going to go ahead and put our times in a line. And what are we going to put on bottom? On top, we're going to put grams of CO2. And that's equal to 1 mole of CO2. Okay, now how do we figure out the molar mass? Again, we're going to add 1 carbon and 2 oxygens. So again, 1 carbon is 12. Okay, so 1 carbon is 12, and then we're going to add 2 oxygens at 16 each, and that will equal 44. So we're going to put 44 grams. Now, again, I want to underline this, and we can put our equal sign in there. Before we go ahead and do the math, we need to cancel out anything that we can cancel out. And again, you can cancel either as we go along, or you can cancel them now. So I have grams of ethylene here, which I'm going to get rid of, and I have grams of ethylene down here. And if you can't cancel everything out, then that means you did it wrong. So remember, 1 has to be on top, 1 has to be on bottom, because anything over top of itself is equal to 1. If they're not over top of themselves, okay, then we can't do that. So you have to make sure that you're putting them in the right spot, and that's one of the best ways. If they're both on bottom, you can't get rid of them. Okay, and we do our last one right here. Now we're left with grams of CO2. Okay, so now we can go ahead and do our math. We got rid of everything else, and remember, what do we do with our math? We multiply by the top, divide by the bottom. Okay, so really it's 45 times 1 divided by 28 times 2 divided by 1 times 44 divided by 1. But remember, when we multiply or divide by 1, it doesn't change the value, so we don't have to do that step in the calculator. So we're going to go ahead and calculate this out. So we have 45 divided by 28 times 2 times 44. And that's going to equal 141.42. 8. So 141.428. Now again, I like to go ahead and double check that. So let's go ahead and double check that again. 45 divided by 28 times 2 times 44 equals, and that's good. So we have to do one thing. We have to go ahead and put it in the correct number of significant figures. How to do that? We go back to the original problem, look at our only number that we have in the original problem, and that's going to be 45 grams. So we have 45. All numbers are significant, so that means that the answer needs to be in 2 significant figures. So we're going to go down here, and we're going to go over 2 significant figures, put our answer. Now again, we got to remember the decimal's over here, so we have to be close to that number. So the 1 says we drop it off, but if I just drop everything off right there, that means that it's only 14. It's not even close to 141. So we're going to put 140, 141, pretty close to each other. Now, do I put a decimal in there? Well, the answer is no. And here's your reason. Because trailing zeros are only significant if there's a decimal. So if I don't have a decimal, that's not significant. So now I have 2 significant figures. And as always, you could put it in scientific notation, but there's no reason to. If I put it in scientific notation, it would be 1.4 times 10 to the second grams of carbon dioxide, which, again, it's easier just to look at this. Go ahead and highlight that. We got it. There's your answer. Okay, for practice sheet number 4, problem number 2. Hey, as always, go Mohawks.